In the 21 years I've been reporting at Intel, I've seen amazing products and the machines that help create them. But the machine I'm about to show you blows my mind. Come with me behind this door and I'll show you. This is it, an EUV, or Extreme Ultraviolet Lithography System. It is likely the most complicated machine humans have ever built. It pushes Moore's Law forward, and chip makers cannot produce leading-edge chips without it. But more on that in a moment. The EUV machine is a reality after 35 years of sustained research and development from lithography leader ASML, Intel, TSMC, Samsung, and others. Delivering just one of these tools to Fab D1X in Oregon took 3 747 cargo planes, 40 freight containers, and 20 trucks. The school bus-sized machine comprises 100,000 parts and weighs nearly 200 tons. So what exactly does this EUV machine do? Intel co-founder Gordon Moore observed that the number of transistors crammed onto a processor doubles roughly every 2 years, a cadence that has continued for more than 50 years and has long been known as Moore's Law. The more transistors and components on chips, the cheaper and more powerful they become. Chip manufacturers use lithography machines to project circuit patterns onto silicon wafers. For decades, they have kept shortening the wavelengths of light on lithography machines to print features for ever smaller transistors. In pursuit of Moore's Law, Intel engineers have produced inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. Intel and other chip makers have also adopted processes such as double and quad patterning and water immersion lithography to get the most out of today's 193 nanometer wavelength light. But to make transistors even tinier, the industry needs lithography machines that use radically shorter wavelengths. This EUV machine produces light at 13.5 nanometers. Compared to today's machines, that wavelength is more than 10 times smaller. So how does this machine work? Put on your best thinking caps and I will try to explain it simply. First, extreme ultraviolet light does not exist naturally on Earth, so we have to generate it. Because this tool is so large, it needs 3 floors in the fab. Its laser, about 15 times more powerful than ones used to cut steel, sits on the level below the clean room. A beam transport transmits the laser pulse up a floor into the EUV machine, where a generator fires tiny droplets of metal tin, each droplet only about 1/3 the diameter of a human hair. And that powerful laser, flashing at 50,000 times a second, hits the molten tin. The metal vaporizes into a plasma. This plasma releases light in the extreme ultraviolet range. A collector mirror gathers the 13.5 nanometer EUV light and shoots it to a scanner, where it pinballs off extremely precise mirrors that shape the light into slits that create patterns of transistors and interconnects onto a silicon wafer. See, wasn't that simple? Just a couple more remarkable facts. Newer factories at Intel have ceilings 16 feet high. They are raised to 25 feet where these EUV tools rest, because it takes an overhead crane system to assemble the heavy system components. How precise are the EUV machine's optics? Here's the math. It's analogous to an astronaut standing on the moon with a laser pointer targeting the tip of my fingertip here on Earth. ASML is already working on an improved version of the EUV tool that will offer even finer resolution lithography. Intel is currently the first customer in line to receive one of these next-generation machines to prepare for the Angstrom era of computing. Isn't this mind-boggling? Hope you enjoyed coming behind this door to see this marvel of engineering and a tribute to human ingenuity. Thanks for watching. I'm Rob Kelton.